so excited. All right, now we're ready. Well, I think we're ready. We're ready? We're ready. We're ready. Billy, I love it. Billy's ready now. See, I've trained him. I molded him. I made him stronger, faster, better than he was at the beginning of the year. Just like you. Just like you. Yes. Now, check it out. So, we broke your self-esteem down, didn't we? And crumbled you onto the ground, little tiny pieces all over the floor at the beginning. But now we put you back together, built you, and look at you now. Look at you. Looking good you are. Okay, I left off with not quite getting to activity because I had to go through decay constants. And from last video, we now know that a decay constant's a probability that one little atom will break down in the next second of time. These numbers are very small because the probability that one's going to break down in the next second of time is not very big. However, you watch it long enough, there's a chance that you watch it for 1 second, it breaks down. Oh, maybe you got lucky there. Or you might be watching it for 10 years, still nothing's happened. Okay? It's just a probability, is all it is. Sometimes you win the lottery and sometimes you don't. Okay, but we also know that it's not just about the decay constant value, which is tied into the half-life. We had our equation on the board. I erased it to make room for our new equation, so it's awesome. And usually we have the half-life equals 0.693 divided by lambda. That was our equation. This is tied in with half-life. What that means is the longer the half-life, the smaller the probability that something's going to break down in the next second, so a very small decay rate. Okay, quick review there. Now, let's get into finishing up what is activity, because we talked about in the last video that it must have something to do with the decay probability, decay constant, and how much of it you have. Remember, if you got a butt ton of it, even if you have a very small probability of one breaking down, if you got a bazillion particles, then probably something's going to be breaking down in the next second. Okay, all right, now, what I got up here is the equation for determining how much radioactive material is going to break down and turn into something new. In other words, this equation here is going to help us figure out those more difficult half-life problems. You see, remember earlier I was saying, half-lives can be really easy, right? 3 half-lives, you have 2 times 2 times 2, 1/8 of the sample left. Easy. Can't we just stick with the Billy? Come on, you've come a long way. Okay, all right. Thank you, Billy. This is the kind of a thing which says, all right, so maybe you've got a half-life of 1 billion years, but you want to know how much of the material break down after 3 weeks. That's what this bad Larry right here is all about. I love this equation. Check it out. So this right here, this delta N here on the left means daughter. It's the amount of daughter or new material that is produced during radioactive decay. Remember, the parent's the unstable one, the daughter is the more stable. We know that's not true in real life, okay? Same. And so this here is the daughter that's created, how many particles, and this is it literally means the number of particles. So how many number of particles of daughter are we going to get from this N here, which means the parent, the amount of particles that we have. Maybe we've got 10 times 10 to the 72nd particles of uranium. And I want to know how much of those particles are going to produce daughter over a time period of 3 weeks. So this is your time period. This is your time period. And this is going to be in seconds. Remember, this has got to be in seconds. So it's not in seconds, you got to get it in seconds. You want 3 weeks. I want to know after 3 weeks how much I have. We'll get that in seconds, okay? You got to get everything into seconds here. So convert. So get this into seconds because our activity or our decay constant here is in seconds, remember. And again, if these decay constants aren't in seconds, you have to get them into seconds, which we showed you how to do in the last video with the half-life equation. Okay, you can calculate that, but make sure your time period for half-life's in seconds, so your decay constant comes out to be in seconds. So this is in seconds. Okay, so this is your decay constant. And so now, if I want to figure out after 3 weeks of time, I have 1 times 10 to the 32nd particles of some radioactive material. And I know it's decay constant. I can then calculate in that 3 weeks how many daughter particles will be made. This one works for those complicated problems. Yeah, you'll get some questions. You'll get some questions that are designed just to see if you know the concept of half-life. And those are easy to solve. But this one here is for those not so easy to solve problems for determining how much daughter is created. Okay, so let's take a look at this though. Check it out. This part of it right here. And the negative, by the way, the negative is just there to indicate that the amount of parent is decreasing over time. So you're losing the parent, it's radioactive breaking down, so you're losing it and becoming daughter. When you do the calculations, you don't have to have the negative in there. It's to indicate that the amount of parent material is decreasing. Okay. So this part of it right here, right there, is called your activity. Now, finally, I can fill this in. Activity is equal to your decay constant times the number of particles. And we've talked about that. I just didn't put it down. Now we're putting it down. Okay, we talked about it. The higher the probability of a breakdown, remember that's what decay constants are, probabilities, multiplied by if you've got a butt ton of particles, you're going to have a relatively high activity. The Geiger counter is going to be going nuts. Now the Geiger counter can be going crackers, like Godzilla crackers, if you have a very short half-life, higher decay constant, or just a butt ton of it, or both. If you have both, you know, a lot of it with a very short half-life, run for the hills. Run to the hills. Iron Maiden, check it out. Up the irons, okay? Heavy metal. Mm-hmm. All right, now, so your decay constant, you know, how active, the decay constant times the number of particles give you how active your sample is. You have an active sample if you have either or both, okay, a large decay constant, larger probability, and a larger number of particles. Okay, so now check this out. This is also going to help you out. In one of our problems we have to solve, okay, rid of this, get rid of this, clean this up. If this is equal to the decay constant, then if I divide the number of daughter times time, that equals that. So that means delta n divided by your change in time. And when I write these out, I don't put the deltas in there. But you do need a change, means you need a period of time from start to finish, and the number of daughter from start to finish. But you can just get rid of those to do the calculation. You don't need those. It's equal to the amount of daughter divided by time. Because if this is decay, then that's equal to n divided by t, right? Yeah, yeah, so both of these are equal to decay constant. You have to keep in mind that this one here and this one is the daughter, and this one here is the parent. So that's your decay constant. Your activity. Your activity, how active the sample is. You know, that Geiger counter going crazy is going to be determined by two things. This is the one we usually talk about. This is the result of it. And then the more daughter that you get produced over a period of time, you have a higher activity. If you've got a lot of daughter produced over a short period of time, you get a big activity, right? And that makes a big number. And so that's the same thing as this one here. But this is here the one we generally refer to when we talk about activity is your probability of breakdown, decay constant, times the amount of particles you have. All right. So armed with that information, there are several problems that we will do using this equation to solve for various things in the equation. Okay, so that is your activity based upon, this is called the, well, I don't call it the half-life equation. I call it like the half-life situation when it's really hard equation. Yeah, you need that. You need to figure out the amount of daughter using this equation here to solve for that. Okay, the difficult half-life equation, put it that way. All right, we'll wrap this video up. Now we're going to go off and you kids do some calculating.